avoid an obstacle, for example, or cross the doorway. We have a specific approach of this man-machine cooperation. We have worked on a software architecture which is symbiotic between the man and the machine. In order to, the man-machine system is considered in a global way, not the man one side and the machine on the other side, but it's one system, the man-machine system. And here, the robot behavior must be only the continuation of the action of the man. And the architecture, software architecture we proposed is decomposed in three parts. First, the planning part, the behavior, and the coordination part. Here, the same, the three parts, the planning, the behavior, and the coordination. Coming back. First, the planning part. The planning part is only the human part. Because the human knows the motivation of the movement. He knows why he wants to move. The person has an inventory of the fixture in the environment. And he knows some specificities of the environment, the danger part, the constraints of the environment, for example. And he has his own emotion. He wants to go to this place because it's his pleasure to go to this place. This is important to realize, to perform the planning of the motion. And the person has some information coming from his ears, his eyes, some information about the environment, the perception of the environment. And every time the output of the person is instantaneous desired action. For example, to go to one direction, instantaneous information. The second part is the behavior part. Here we have a set of behaviors. The robot is able to perform some behaviors. There is some problem. What is this? Yes. Each behavior has a bottom-up structure. A bottom-up structure, we have information on the environment and perform an action. And here, each behavior of the robot works parallelly and in an independent manner. And each behavior here is an agent. And we are in front of a multi-agent system. And now it's a robotic system. And the last part is a coordination part, is every time the robot part. I said that the robot is a set of an amount, a sum of behaviors, but working parallelly. But what is the best behavior in a given situation? And this is this part which selects the best behavior for one given situation. And this module here gives two outputs in terms of velocities, linear and angular velocities. I want to come back to what is behavior. Behavior is composed of different knowledge. Knowledge about the structure of the environment, for example, the position of the walls, the position of the obstacles, the direction the person wants to follow, is the output of the person, of the plan of the person, and short-time memory, what happens in the past, and some information which gives relation between the environment structure and the different outputs coming out from this behavior. And there are two outputs of this system, of this behavior. First, the information for controlling the wheelchair, the different velocities, linear and angular velocities. But also another information is the relevance for this behavior in this situation. And this is compute, I don't have a pointer, this is compute in this part here. You don't have a pointer? No. I think I have a part here. Yes. Is this part here define the ideal observation, ideal information coming from the environment for using this behavior. And every time each behavior compute for itself the best, an information that qualifying and quantifying the relevance to use this behavior in this situation. And the behavior is composed, the architecture of the behavior you can see on this slide. It's not big enough. 3 inputs. First is the state of the system. I want to go in detail later. I cannot read. Yes. Short memory informations, the second. And the last is the different relation between the information sensed and the action to the environment. And this is called the iNOT behavior. Each iNOT behavior outputs velocities, angular and linear velocities. And in the second part, on the bottom here, is the assessment of this behavior used in the present, in the actual situation. And this is the information qualifying the relevance of this behavior. It's important information. There are 3 types of iNOT behavior. Reflex behavior, following a vector behavior, and the stop behavior. Like a baby and child, then born is the same kind of behaviors. The reflex behavior, the objective of this behavior is to avoid obstacles. So system states are in 3 points. First, information coming from the environment. Here we use the old technology with ultrasonic range sensors, but we have implemented laser scanning, but it's the same information and can work in the same manner. The second information of the state is structured information. Where are the obstacles? In the front and the back, on the left and right, for example. And the third information needed is the direction the person wants to follow. I want not to go into detail, but the different information coming from the sensor are gathered, and we compute the angular velocity given by this expression. Each sensor has a static contribution to the obstacle avoidance. And this static contribution is weighted by the inverse of the distance measured to the obstacles. And this expression, mathematical expression, gives the angular velocity for avoiding the obstacles. And the short time memory is very important in this situation because we use ultrasonic sensor, and ultrasonic sensor has some drawbacks. The specularities are some drawbacks. But the information we can measure is not available at each time. And because this information, we use this expression in order to take into account the memory of the measured information, and in order to cope with the problem with specularities. The vector following behavior, the second behavior, is only a system that tries to follow a vector. The vector may be defined by anything. For example, if you want to follow a wall, the vector is parallel to the wall, for example. If you want to follow a specific direction, the vector is defined by the specific direction. And with a system, with a technology of fuzzy logic, we compute the best angular and linear velocity. And what is very important is to assess the behavior, to evaluate the relevance of one behavior in one situation. As I said, each behavior is independent, is a structure like threads, and each thread is working independently. And we must compute which is the best behavior in one situation. And according to some information, the environment configuration, the state of the system, and the direction the person wants to follow. And with a very simple equation, which is a computation of similarity between two vectors, the state of the environment and the ideal situation. I spoke about this, the ideal situation, and if we realize this similarity computation, we find information that qualify the relevance of the using of this behavior in this situation. And the coordination part, is the last part, concerns the selection of the behavior. All behaviors are computed parallelly, but now we must select the best. It's only according to the relevance value, how I have computed in the previous slide. But there are some priorities between this behavior. First, the stop. Person wants to stop. Second, the reflex behavior to avoid obstacle. And then follow a vector behavior. We have implemented this symbiotic architecture on a wheelchair. And this wheelchair and this project is called VAM, French acronym for automated vehicle for motor disabled person. We have two versions on the left. The first version is a power push wheelchair, and the last one on the right is Storm from Invacare wheelchair. We have the basic system, the basic control of the wheelchair, and we have added a PC connected to the basic control system. On this wheelchair, we have implemented some behaviors. The stop behavior, no problem. Some behaviors which inherits from follow vector, init behavior. 5 behaviors: follow the left wall, follow the right wall, follow a direction, go backwards and a bit left, go backward and a bit right. And behavior which inherits from reflex behavior, obstacle avoidance behavior. And we have implemented this on the wheelchair I show you. And for example,